Hello everyone, myself Mohesh Gowda. I'm currently studying Electronics and Communication Engineering from Sri Venkateswara College of Engineering. Today I'm gonna be making a video on mathematics. The topic is curve fitting with the least squares method. Curve fitting is a fundamental concept in data analysis and statistics. It involves finding a mathematical function that best represents the relationship between a set of data points. The least squares method is a powerful and widely used technique for achieving this goal. This presentation explores the principle of curve fitting and dwells into the working of the least squares method, providing insights into its practical applications. Introduction to curve fitting. What is curve fitting? Curve fitting is the process of constructing a curve that best represents the relationship between a set of data points. The curve can be linear, polynomial, or even more complex functions, depending on the nature of the data. The goal is to find a curve that minimizes the deviations between a fitted curve and the actual data points. Applications of curve fitting. Curve fitting finds applications in various fields, including data analysis, statistics, engineering, and finance. It is used for tasks like predicting future trends, modeling physical phenomenon, and identifying patterns in data. Examples include foresighting sales, optimizing production processes, and analyzing market trends. The least squares method principle. The least squares method aims to find the curve that minimizes the sum of squared residuals. Residuals are the differences between the actual data values and the values predicted by the fitted curve. Minimization. By minimizing the sum of squared residuals, the least squares method ensures that the fitted curve comes as close as possible to all data points. This is why it is called the least squares method. It aims to minimize the square of the errors. Optimality. The least squares method provides an optimal solution, meaning it finds the best possible curve within the chosen function family. This ensures that the curve accurately reflects the underlying relationship between the data points. Formulating the least squares problem. Data points. The first step is to define the set of data points. Each data point consists of an independent variable x and a dependent variable y. These points are typically represented as xi, yy, where I is an index ranging from 1 to n, where n is the total number of data points. Fitted function. Next, we choose a function that we believe best represents the relationship between the independent and dependent variables. This function could be linear, polynomial, or even more complex functions. The function will have unknown parameters which need to be determined. Residuals. The residuals are the differences between the actual dependent variable values yi and the values predicted by the fitted function yi dash for each data point. Mathematically, the residuals are calculated as Ri is equals to yi minus yi dash. Sum of squared residuals. Finally, the sum of squared residuals is defined as the sum of the squares of all the residuals. This represents the total squared error between the actual data and the fitted curve. Minimizing the sum of squared residuals. Mathematical optimization. To find the curve that minimizes the sum of squared residuals, we need to find the values of the unknown parameters that result in the smallest sum of squared residuals. This involves using mathematical optimization techniques. Calculus and derivatives. Calculus and derivatives are essential tools for finding the minimal of the function. We calculate the partial derivatives of the sum of the squared residuals with respect to each unknown parameter and set them equal to 0. Normal equations. Solving the system of equations formed by setting the partial derivative to 0 leads to a set of equations known as the normal equations. These equations can be solved to find the optimal values for the unknown parameters. Solving the normal equations. Matrix representation. The normal equations can be represented in matrix form, which simplifies the solution process. The matrix form provides a compact and efficient way to handle multiple unknown parameters. Solving for parameters. By solving the system of normal equations, we obtain the values of the unknown parameters that minimize the sum of squared residuals. These values determine the specific curve that best fits the data. Numerical methods. In many cases, solving the normal equation involves using numerical methods such as matrix inversion or Gaussian elimination. These methods provide numerical approximations to the optimal parameter values. Fitting linear models. Equation. A linear model is a function of the form y is equals to mx plus c, where m is the slope of the line and c is the y-intercept. These parameters represent the relationship between the independent and independent variables. Normal equations for linear models. Applying the least squares method to a linear model leads to a specific set of normal equations that can be easily solved for the slope m and y-intercept c for the best fit line. These equations provide a closed form solution for linear models. Applications of linear models. Linear models are widely used in various fields due to their simplicity and interpretability. Examples includes predicting sales based on the advertising expenditure, analyzing the relationship between temperature and pressure, and understanding the impact of fertilizer on crop yield. Fitting polynomial methods. Polynomial equations. Polynomial methods are functions of the form y is equals to a0 plus a1 x plus a2 x square plus continuous going on, where ai are the coefficients and the n is the degree of the polynomial. Normal equation for polynomial models. The least squares model can also be applied to polynomial models, resulting in a set of normal equations that can be solved for the coefficients of the polynomial. The complexity of the equations increases with the degree of the polynomial. Flexibility and complexity. Polynomial models offer greater flexibility than linear models. They can capture more complex relationships between variables, but they also become more complex to fit and interpret as the degree of the polynomial increases. Accessing goodness of fit. Coefficient of determination R2. R2 measures the proportion of variance in the dependent variable that is explained by the independent variable. It ranges from 0 to 1, with higher values indicating a better fit. Root mean squared error (RMSE). RMSE measures the average difference between the predicted and actual values. Lower RMSE value indicate a better fit. It is expressed in the same units as the dependent variable. Standard error. The standard error measures the variability of the fitted curve. A lower standard error indicates a more precise fit. It is expressed in the same units as the dependent variable. Conclusion and key takeaways. The least squares method is a fundamental technique for curve fitting. It provides an optimal solution by minimizing the sum of squared residuals, allowing us to find the best possible function that represents the relationship between data points. By using the least squares method, we can accurately model trends, predict future outcomes, and gain valuable insights from the data. Understanding the principles and applications of the least squares method is crucial for anyone working with data analysis and statistical modeling.